Okay, here we are with another calorimetry question. Not combustion this time. Note that here we're carrying out an actual chemical reaction. So we're finding an actual enthalpy of reaction. In this case it's an acid-base reaction, so it's an enthalpy of neutralisation. But first thing to check is what's going on. Are we burning anything? No. We are mixing together two chemicals and we're measuring the temperature of the mixture. So again, we're going to have to make some assumptions here. It doesn't ask us to make any assumptions in the questions, but it's always a good idea to include any assumptions that we make. Well, let's start by finding out how much energy was released in the experiment. We know energy was released because the temperature has increased. So we do know that this is an exothermic reaction. It's exothermic. So Q is equal to mc delta T. And all those values, mc and delta T, all refer to the substance that's having its temperature measured, which is the solution or the mixture. The mixture that we have after mixing the potassium hydroxide and the hydrochloric acid. Well, we're not given masses, but we are given volumes of the two solutions. And the total volume is the one that has its temperature measured with the thermometer, which is equal to 50.0 plus 50.0, which is equal to 100.0 cubic centimeters. So now we have to make an assumption. We're going to assume that the density is equal to the same as water, 100 grams per cubic centimeters. So we can imply from that that the mass of our solution is equal to 100.0 grams. Remember, most of the solution is in fact water. They're aqueous solutions, so there's no problem with making those assumptions. We can also assume that the specific heat capacity of our solution, C, is the same as water, 4.18 joules per gram per Kelvin. And the temperature change, well, we've got that over here. Change in temperature is equal to 23.1 subtract 19.6, which gives us 3.5 Kelvin. Now, something to note here is that could be considered a bit of a problem with this experiment, because as we've only got a very small temperature change, we've only got two significant figures for our temperature. That's going to limit how many significant figures we can use in our final answer to a maximum of 2. When we're planning labs, it would be much better if we had a greater temperature change to increase the number of significant figures we can give in our final answer, and of course then the precision. Well, let's find out then what Q is. Q is equal to our mass, 100.0, multiplied by our specific heat capacity and our temperature change, and that gives us 1463 joules. Now, we're not given, as we were given in the combustion reaction, we were burning a certain mass of fuel, so finding the number of moles of fuel was a case of having the molar mass and the mass in grams. Here though, we're using solutions which have got volumes and concentrations. Volumes and concentrations. If we remember from way back when we did quantitative chemistry or stoichiometry, number of moles is equal to the concentration of a solution multiplied by its volume. And as concentrations are usually given in moles per decimeter cubed and volumes in cc's, we tend to divide by 1,000 to convert the units. So we can see that for both the acid and the alkali here, the KOH and the HCl, they both have the same volume and they both have the same concentration. So the number of moles of both, the number of moles of acid, which is equal to the number of moles of base here, is equal to the concentration multiplied by, let's give the correct number of sig figs, the concentration multiplied by the volume divided by 1,000, which gives me 0.025 moles. Now, from there, if we look at our chemical equation up at the top again, we can see that the ratio is 1:1. And so as we've got the same number of moles of each, they are both the limiting reagent. That means now that when we're trying to find delta H being equal to Q divided by N, we're going to use N, the number of moles of the limiting reagent, to find our per mole value for the enthalpy change. So how do we do that? Then delta H, we know that it's exothermic. We decided that right at the beginning. So delta H equal to negative 1463 divided by 0.025, which gives me negative 58250, which if I round up to the correct number of sig figs and divide by 1,000 to give me kilojoules per mole, I end up with negative 58 kilojoules per mole. Thank you very much.